Welcome back, everyone. This is our second video on nodal analysis, and in this video I would like to focus on the second half of nodal analysis, which is essentially how do we form the matrix for the nodal analysis and how do we solve the unknown nodal voltages. Let me very briefly review for you what we are doing in nodal analysis. In nodal analysis, we are attacking a circuit by literally first labeling all unknown nodes. This is the circuit I used in the previous video, and here you can see that I have labeled all my unknown nodes, V1, V3, V4, all the way to V5. So let me write the first step is to label all unknown nodes. Then the second thing that we did is we wrote KCL for every node. Now, let me make one point here as emphatically as I can. You need to be able to apply KCL for every node exactly the same way in exactly the same consistent way. You have to be able to apply KCL consistently, which means sum up all the currents that leave this node to come back to zero. So you treat each node independently, and for each node you apply KCL, summing up all the currents leaving to zero. This will give you a bunch of equations, which we'll review in a minute. Once you get those equations, the new steps, which we're going to learn today, is how do you place them in a matrix form. And then we will briefly discuss solving for any other quantity that you want. So let's go ahead and look step number 3. So these are the nodal analysis equations that you would get if you take the circuit that I gave you before and you write nodal analysis in exactly the way I suggested, meaning summing all the currents out of the node to be equal to 0. You'll get one for node 1, node 2, and so on and so forth. Now, the next natural question is, okay, fine, you gave me the equation, or I can write down the equation, I get how to do it. How do I solve them? Well, if you pay close attention here, you basically have 5 equations that you're dealing with, and you have 5 unknowns. So it's essentially a system of equations. It's a 5 by 5 system that you have to solve. And of course, you can use the good old method of substitution, but honestly, this will lead to a lot of unnecessary algebra. There's a much better way to deal with that, and the much better way to deal with that is to essentially write these equations in a form that is closer to a matrix form. What do we need to do it in a matrix form? We need to basically have something times unknown 1, which is V1, plus something else times my second unknown 2, plus all the way plus something else times unknown 5 is equal to something that is known. Right? That's what I mean closer to a known equation. That's not exactly written the same way here. It's very close. So if you follow this idea, you will get this set of equations. These are exactly the same equations as you saw before, except that now I basically wrote some known coefficient times the first voltage, unknown voltage, plus some other known coefficient times the second unknown voltage, all the way until I have all the voltages in my node. And then finally, I have something known on the right-hand side. You can do this thing for every single node in your circuit. In this case, I have 5. And so I have basically done this thing for all 5 nodes. Now, once I have my equations in this form, and it really doesn't take much to write them that way, then I can basically go ahead and put them in a matrix form. What does matrix form mean? It means you will have basically all the known coefficients in a matrix. You will have all your unknowns in this vector here. And then you will have on the right-hand side a known vector. For example, in this case, the known vector will be IS1 from the first node, negative IS2 from the second node. So it's this one, IS4 from the third node, negative IS3 from the fourth node, and negative IS4 from the fifth node. So this will be your vector of knowns. Now, you can very quickly do that. So, for example, this first coefficient here is going to be the coefficient that you have on the node V1. So, it will be 1 over R1 plus 1 over R2 plus 1 over R8. Let's see the final expression here. So, this is the final expression that I have for my matrix form. So, I have my G form. I have my unknown vector V, which I have called it V with a little bar on the top, and then I have my known vector I, which has basically all the known vectors. So if you don't really recall multiplication of matrices with vectors, I would strongly recommend that you check online or check your old books how you can basically do that. There are tons of extremely good videos online and very quick notes that can refresh your memory of how do I multiply a vector with a matrix. And essentially now you have the equation that G, which is your matrix, times the unknown vector V is equal to the known vector I. What is the solution for that? Well, the solution for that is that V, the unknown vector, will be equal to the inverse of G, which I'm calling G to the power of -1, times the vector I, which is the known vector. So from a formal point of view, you can write the solution like this. From a practical point of view, you have to be able to calculate the inverse of G. Now, if you have ever calculated inverse of matrices, you know that this is probably not the most pleasant experience in life. But nowadays, we have a ton of tools that can do that in an instant for us, both in a numerical form as well as in a symbolic form, which is the form that you see right here. So either you can use your favorite tool, maybe, I don't know, MATLAB or some other tools, or you can use essentially something online. There are many websites that you can just literally type the matrix you have here, click a button and get the equation you need. So once you do that, you will be able to get exactly the unknown voltages V. And so you will get that the vector V is going to be equal to some number, another number, all the way for the fifth one. And now you basically have calculated all your unknown voltages. And as I mentioned in the previous video, in the last step, once you do have all the calculated voltages, then every single power or current can be found. For example, some unknown current Ix will be equal to perhaps V1 minus V2 over R8. I'm just making up the numbers here. This does not represent the previous circuit. My goal is to show you that any current you want will be calculated by some type of a voltage drop divided by resistance by using Ohm's law, or any kind of power you have, it will be V2 minus V4 squared divided by R9. Again, I'm making up numbers here. It's not the previous circuit, but again, my point is to show you that voltages and voltage differences can be used to find powers that you need. So that's basically the idea. That's how we go from the nodal equations that are written here in more of a raw form to writing them slightly better way. So we're ready to put them in the matrix form, and then here's the matrix form, and then a simple inversion will give you the answer. Now you might say again, what about if I just follow the method of substitution? Again, you can do it. It's just a lot more work. It is far less systematic. So I would strongly recommend that you use the matrix form, particularly if you have a circuit that has more than 2 nodes. If you only have 2 unknown nodes, yeah, no big deal. Just go ahead and do it. But if you have more than 2 nodes, this is a far superior methodology. So thank you for watching this video, and I hope you'll have a chance to practice this yourself. I have emphasized in previous videos how important it is to not just watch these videos and think that you're getting the point. It's far more useful for you to use those videos, but do the exercise yourself and simply come back and check the result. I hope you do it. I sincerely hope you do. You will learn a lot more. Thank you very much. See you next time.